So last time we talked about power, we talked about calculating power from sample size. That is, you've already run an experiment, maybe you didn't find anything, and you're wondering if you didn't find anything because your experiment didn't, the number you had recruited into your experiment didn't give you adequate power to detect a difference if it really did exist. So that's one use of power. The other use of power is to be able to calculate sample size, to decide how many participants you need ahead of time before you start your study to have adequate power. So rather than maybe something going wrong and you're checking to see did you have power to be able to detect a difference, you start before you actually do your study to figure out how many participants do I need and to be sure that I have adequate power to detect a difference if it really is there. So the formula for calculating sample size based on effect size and power is n, and the n is going to be the total number that you need, equals 2 multiplied by delta divided by effect size squared. So to sort of plug in some numbers and see how that formula would work, one example is how many participants would be needed for an experiment with two groups and a power of 0.80. Now the power statistic that we're using there, the number, is kind of like the effect size, where there's no hard and fast rule. You can change that number, but we figure an 80% chance of detecting something, if it really is there, is a pretty decent chance. So we're setting the power level at 0.80, just as we tend to set our effect size at a medium effect size, 0.50, just by default. Again, there's nothing written in stone about those numbers. You can change those numbers around to try different values and see what you get, but just as a sort of Zen middle path, a power of 0.80, 80% is pretty decent, and an effect size of 0.50, medium effect size, if you don't actually know the parameters, it is a pretty decent value to sub in. So we have to figure out for a power level of 0.80 what is our delta. So we go back to the table that we used for the conversion of power to delta and delta to power. So again, this is delta, and we decided we want to use a power level at an alpha of 0.05, our sort of gold standard that we use. So we have to find a delta of we have to find a power level of 0.80. So we go down the column and we find the power level of 0.80, and we look over to the corresponding delta, and the corresponding delta is 2.80. So a delta of 2.80 corresponds to a power level of 0.80. So we go back to our formula and we plug in those values. So 2.80 is the delta value we plug in, and we said we're going to use a medium effect size of 0.50, so we plug that in here. You divide 2.80 by 0.50 and you get 5.6. You want to square that and multiply it by 2. When you square 5.6 and multiply it by 2, you get 62.72. Or we can round up to 63. But we said we have an experiment with two groups. So since there are two groups, we have to add 63 to 63. 63 would be what you need in one group. You need 63 in the other group. So this would give us an N of 126, or that we need 126 participants in our study with these parameters to be sure we have adequate power to detect a difference if it really is there. Again, you can sort of sub in different values. If you maybe want a power of 90%, you sub in 0.90. If you know that there's a particular effect size as a relationship between two variables, you might plug in the effect size, but in the absence of knowing those, you kind of sub in those default parameters. And the effect size and the formula will change depending on which statistical test you're using. And as I mentioned in class, there is software out there that will do this for you. So I'm sort of running you through the numbers and giving you an idea of how all this works. But in a practical sense, we're going to be using G-Power software in class to actually take the parameters of your study and do a power analysis based on it. So you won't actually have to hand calculate it. There is software now that will do that for you.